We are using a lot of tools and equipment. It's kind of high tech. Some of the tools are called microsurgery, for chips. You get like to get so much knowledge about the hardware and the embedded firmware that suddenly it gives you access to more tools. So we are opening doors in a way. So the way I see it is we take black boxes and we convert them to, I would say, gray boxes, part of the hardware is known, part of the firmware is known, and from that, you can start to do whatever you want. So I say whatever you want because the end goal to me is very broad. So for the hackers, it can be like emulating a device, cloning a device. But for the security researcher, it's finding vulnerabilities, backdoors, looking for the supply chain, and these kind of things. Working in digital forensics is a big thing too. So you try to extract secrets that people will use in a broader scope. So we go from chip, we extract secrets, and people are using this for working on the device, basically. So this is where we are when we do chip hacking, I would say.
Optical microscopes, electron microscopes, focused ion beams, thermal imaging cameras, X-ray machines, CT scanners, precision tweezers, nitric acid. Sounds like a high-tech hospital R&D facility, right? Well, actually, no. Today, we are going to be talking about IC reverse engineering or chip hacking. And these are some of the tools and equipment that is required to be able to successfully hack into chips. So welcome everyone to the JHacker show, where we talk pure tech and the practical implications of security issues, cutting the noise. And today I have with me my best friend and one of the most or the best chip reverse engineer or hacker in the world, Olivier Thomas.
Hey, thank you for having me.
Welcome to the JHacker show, Olivier.
I'm pleased to be here.
So I've always been curious about how do you hack chips. So when you talk about hardware security, it's actually a pretty broad industry in say. So you have device hacking as a practice, which is more on the functional security side, and then you have bootloader, kernel, firmware hacking, which is more or less software hacking, software reverse engineering tied to the hardware. And then at the lowest level, you have, bare bone silicon hacking. So I'm always intrigued by, all these different techniques that folks use to hack chips and find vulnerabilities. So for our viewers, I just want to understand what are the vulnerabilities in these chips and how do you go about, reverse engineering chips at a high level, and then we'll deep dive into each of the different techniques that people use.
All right. Yes. It's a very broad question, but let me put it this way: like when we are dealing with chips, it's usually the chips comes from a device, But sometimes when you want to have like information about the device, you want to first know what the chip is doing. So I see chip hacking as a way of getting information, first of all, not necessarily to get like a final hack, but to get the information. And I think the best example of this, and I think it's also where the people start when they start to do like chip hacking, is like getting boot RAM out of chips. Because suddenly, if you have like let's say a secure element or a secure chip, it can be an SoC, a smart card, or a secure element, broadly a secure element, let's say. If you extract the boot RAM, suddenly you get knowledge about what's happening inside the chip. It's not a black box anymore. So being able to extract the data from the chip, and I'm speaking boot RAM, but it can be also extracting the flash, the fuses, and so on, memories in general. But suddenly you have enough knowledge that you can understand what's going on. and you might be able to, create a very simple attack that's based on that. If you have knowledge about the software that's running on your chip, it becomes easy to know where to glitch, when to glitch, and this kind of things. So as you said, it's like we are using a lot of tools and equipments. It's kind of high tech. Some of the tools are called microsurgery, for chips. And basically, yeah, you get like to get so much knowledge about the hardware and the embedded firmware that suddenly it gives you access to more tools. So we are opening doors in a way. So the way I see it is we take black boxes and we convert them to, I would say, gray boxes. Like part of the hardware is known, part of the firmware is known, and from that, you can start to do whatever you want. So I say whatever you want because the end goal to me is very broad. So for the hackers, it can be like I don't know, emulating a device, cloning a device. But for the security researcher, it's finding vulnerabilities, backdoors, um, looking for the supply chain, and these kind of things. Working in digital forensics is a big thing too. So you try to extract secrets that people will use in a broader scope. So we go from chip, we extract secrets, and people are using this for working on the device, basically. So this is where we are when we do chip hacking, I would say.
Okay. So on a broader scope, you would say that the use case for reverse engineering would be from a forensics perspective, and finding vulnerabilities within the chips themselves. Yeah.
Yeah, for example, yes, yes. I can give you an example. Let's imagine you have a chip, it's a black box, you don't know what it's doing, but there is a secret embedded in the flash. Could be a piece of firmware, could be cryptographic material, could be anything, but you want to access this thing. Let's say now that you have the capabilities of extracting the boot ROM, and suddenly you realize that during the boot sequence, you have like hidden modes of operation for the device that would give you access to the secrets. Now, for you, it all becomes I mean, like what you are looking for now at this stage is you need to just like make sure the chip will jump in this hidden mode, and suddenly you have access to the secrets. And from this, then I don't care anymore. My job is to work on the chips, but in general, people will want to have like knowledge of the firmware or extract a key or things like this. And from this, we provide the necessary information to reach this stage where then you can go further and hack the device. So multi-stage operation.
So when you say hidden, uh, would one use case be to look at backdoors in the chips as well?
It could, yeah, yeah, yeah. So backdoors could be embedded in the firmware. So that would actually, it's not really a backdoor. It's a backdoor that would be there for the chip manufacturer, for example, to program the chip in the first place. But it could also be like in the hardware itself. So you hear more and more people talking about the supply chain security because you design your chip and then it's manufactured somewhere else. But in the process, the guys have the files to produce the chip, but they can modify it, to introduce a backdoor. So this is also something that we can search for. So we are looking for the backdoor at the hardware stage. But then, as you extract the firmware, you can also analyze the firmware to see if you have other backdoors in the process. So it's again when you are at a very low level. So chip is very low level, I guess. You can look for all of this. So it's not easy operations, but it can provide a lot of information.
That's interesting. So given when you're talking about backdoors, what kind of backdoors would these be? Like, given that a manufacturer has a design spec for a chip and it gets manufactured at a third-party facility, is there only way to inject backdoors would be to put malicious or add malicious code, or can you also change the design somewhat, or inject some kind of a hardware backdoor per se in the chip? Are both possibilities?
Oh yeah, of course, yes. So there was a paper. I think it's pretty old now, and I wouldn't be able to tell you where it's coming from. But they were speaking about like privilege escalation, and the thing was that they modified the circuitry, adding few transistors here and there, and then you had to stimulate one of the I/O pins in a very particular pattern, and then you would have like the privilege escalation. So that's one possibility. And I think nowadays the big players, they want to validate that their chips are backdoor free. It's mandatory for them because of course it's a critical. I think silicon is a critical asset in this sense. Modifying the code might be a bit more complicated, especially on secure chips, because usually the code is encrypted and so on, so that would require more. But the code, I mean, like, if you have the chip vendor, you need to program the chip in the first place. So it means that you need to have some kind of a way of injecting code inside, right? In general, in the flash memory. And if you do so, you have also a way of extracting the code, because if I program the chip, I want to be able to verify that I programmed it correctly. So it means that in some chips, you have a way that lets you program the chip, but also read the chip out. And in general, those things are not accessible anymore when the chip is in production. But this is where we come into play, because if we can find those modes and we can like make sure that we trigger something in the chip that will jump to this mode, then you have access to this. So backdoors can be the two things, software or hardware. And the software one, it might not be called a backdoor, because if the chip vendor is getting this mode, programmation mode or something, it makes sense. It's not really a backdoor, but you're not supposed to be able to use it. But this is when hacking is a nice thing because you can re-enable those functionalities, for example. The hardware backdoor is malicious, and to me, it's a emerging threat. So I know people are talking about this since quite some time, but it's complicated. If I give you a design and I tell you modify the design to introduce a backdoor, it's not an easy task, but it's a threat anyway. So people needs to validate this and make sure that their chips are okay, so usable, sure, safety, security, all those things.
Okay. So when you say it is difficult, let's say given a design, it is difficult to inject a backdoor. I would want you to define the difficult part here. Is it kind of a probability where, let's say, it might be possible, it might not be possible because of certain scenario, or it is too much work, but it's possible?
Well, it's a question of it's a question of work basically because when you get like the design files, you don't have like the schematic basically. You have like the mask file of the chip. So how the transistors are placed, where the tracks are to connect all of this. So in a way, you need to reverse engineer this to make sense of it, to understand how the chip works. Now you need to modify this, but if you modify the design now you need to simulate it again and make sure that it's gonna work. And the chips nowadays, that's a lot of transistors, and they all need to work. So it's difficult. So I would classify this as a very high-end attack, for the attacker because it requires a lot of expertise and knowledge. So I don't know. People would say I have a friend that would say it's a space attack, like. But like if you have a group large enough working on those topics, it's feasible. In theory, it's always feasible. But now you need to have a good team for this. So it's not an easy process.
Okay. But it is possible.
It is, yeah.
Okay. Yeah. That's what I wanted to hear.
Don't do it.
So, I mean, when people talk about hardware backdoors, I hear people talking, most of them are talking about, the board level backdoors where, okay, they will put a component that can, you know, get data and then transfer it somewhere, do some unauthorized stuff. But But as you mentioned, that that it is also possible to have backdoors inside the chips as well. So that
Yeah.
makes it more scary, right? Because that is, once you have it, it's extremely difficult to then reverse engineer and identify whether there is a backdoor or not.
Yes, it's very
Oh,
difficult. I mean, like if you place the backdoor directly inside the chip, it's very difficult to see. I mean, there's no extra chips on the board and stuff like this. So now, if you want to find the backdoor, basically you need to compare your design with the original design. So this is where problems arise because, in a way, like for example, if we are asked to find or to evaluate if a backdoor has been injected, first of all, we need to have something like a golden sample. We need to have the mask file from the chip vendor, and usually they don't give this to you. Can we get your files? It's no. So it means that you need to find the chip that you can consider as like the reference design. Like this one has no backdoor. And now you need to take like a chip that you find you buy basically. You buy a chip and now you need to deconstruct the chip and reverse engineer the chip to the point where you're capable of like making a difference between the mask. And I don't know a lot of people that can do this because now it requires to have like the lab, the reverse engineering capabilities, and so on. It becomes a very complex problem to solve. So hopefully at Explain, this is what we do. But we are not so many companies doing this kind of assessment, and it's not an easy task. Of course, I mean, speaking about Explain, we are working on processes to make this like fast and efficient. But still, it's not something that I would call easy. And the main difficulty will still be how to get the golden sample. This is the key.
okay. Okay. Um, okay. A stupid question here. Is power analysis or timing analysis in terms of running code, is that a way to be able to identify whether the chip is backdoored if you have like a reference chip and then one that has come from the third party?
It can be, yeah. It's a valid method. Generally, I would say it's much cheaper than going through like the full chip reverse engineering. But in terms of coverage, you can't test everything. So the privilege escalation attack I was speaking about, for example, the way you had to stimulate the I/O, I don't know. Do you want to do some kind of hardware fuzzing on the chip for weeks, to maybe not find it? Maybe you just don't find it. The chip is behaving normal to you. But now, if you look at the actual physical device and you study it, you would say, yeah, but there is this extra part here. And this is the backdoor actually. So. It's complementary methods, but I wouldn't say that with side channel and power analysis, timing analysis, and so on, you would be able to have like full coverage. If you do physical analysis, you have full coverage, but it's more complex, of course.
Hmm. All right. So,
Yeah.
You mentioned side channel analysis.
Yes.
So for our viewers, can you explain a bit in terms of what is the purpose of side channel attacks or analysis, and what can you achieve with side channel analysis other than what is commonly known that, okay, you would use that to I find encryption keys by power analysis. Is there any other use case for side channel analysis from backdoor perspective, or any other kind of vulnerabilities?
Probably. I mean, like that's not what we do, but I can pretty easily imagine. Like you can build some kind of templates. You stimulate your chip and you measure, for example, the power consumption to see how the chip behaves in such a test case. So you can compare several chips. Again, you still have the problem of the golden sample to me, because what's the non-backdoor sample? Well, it's difficult to know. But you can do this. You can do power analysis to get like some information about what's going on. You could also use like more fancy side channels. Like why not doing photo emission So photoemission is the principle that when transistors are switching states, they emit photons. So basically lights. So if you have a camera sensitive enough, you would see the active part of your device and you can compare again. So it's always based on comparison, those kind of techniques. And there are so many side channel, EM side channel. I mean, you name it, it's very broad, But you have always the same issue of getting the golden sample first and then coverage, because you don't know what is activating the backdoor. And if you need to do some kind of fuzzing to find the activation of the backdoor plus the side channel to prove that there's a backdoor, it becomes a very time-consuming and difficult problem to solve again. So that's why I mean, we are specialized in IC reverse engineering. So I'm biased, but that's why we go on the physical side of things, because I mean, like when you see the transistors and the routing of the transistors, it can't lie. It's there. It's physical. So you see it or you don't see it. So if I find something extra or something that has been removed, I can go and I can get a netlist of this difference and say, okay, so now I have extra transistors on the device, and this is what they do. And that's probably the backdoor. So you can now analyze the backdoor. If you do side channel, and let's say you can prove that there's something bizarre going on, you will not be able to characterize it. You would say, oh yeah, there's this extra noise or something that's bizarre, but what is this? And then you're stuck here. You need to find how to activate the backdoor, and yeah, that's again some work to do. So yeah, there's no good way in a way. You do side channel, you can't have like full coverage, or you go physical. Now it's long and difficult, but you have full coverage. So you need to make a choice. This is the industry, I guess, making choice.
All right. So given a chip, let's say I give you a chip, from there to reaching an objective, let's say to be able to extract code out of it or extract keys out of it, can you walk us through the steps and the process and some of the equipments that I mentioned? What is the use? What problems do they solve? Step by step, like, okay, I got a chip, now what? Then if I do something, then next step, what?
So yeah, of course I can do this. So in general, I would say, so if I'm right, that's 4 steps, right? Step number one is in the lab. So you need to basically deconstruct the chip physically. Okay, so now you are in the lab and you have to use acids. You need to use like failure analysis equipment to have all of it at once. The idea is now to be able to a chip is basically some kind of a stack of layers. All of the upper layers will be interconnect as a PCB in a way. And the lowest layer will be the standard cells and most likely the transistors. Okay, so the active part is at the bottom and the rest is just interconnect. But you need now to be able to see them all, right? So in the lab, what we do is called deprocessing. Sometimes you can see delayering because you remove layers. And so you need to remove every of those layers one by one. And then you will use a microscope, a scanning electron microscope, to take pictures of the layers. So you end up with like thousands of pictures, tens of thousands of pictures, hundreds of thousands of pictures per layer. You need to reconstruct this, so to get like a picture of the full layer. And then you need to remove the layer to get to the layer below and do the same thing. Take pictures, boom, 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 and you remove the layer, take the layer below, and you do this for all of the layers of the chip. If you can do this correctly, at the end you have one picture per layer, and if you can align them together, you go to stage 2 of the process. So stage 2 is going from the pictures to the schematic of the chip, right?
Oh,
Because
okay. Before moving to step 2,
yep.
well, in the step 1, you mentioned that you will use acids, okay, nitric acid or whatever acid. So one is you need to be very careful. You need to have a setup, otherwise you're going to kill yourself, right?
Yeah, don't do
Yeah.
this in the kitchen. Yeah.
So So when you apply the acid, aren't you destroying part of the chip, which means the
No,
layers itself, or is there something on top of the layers also?
no, we destroyed the things. It's a destructive process. Stage one, you will kill chips. That's the idea. So you use acid, okay? So generally you use the acid. So you mentioned nitric acid. Nitric acid is good for removing the epoxy. So basically your chip is packaged, and to remove the package, you drop the chip in the nitric acid to get rid of this, right? So now you have the silicon, the chip itself. The top layer of the chip will be what's called the passivation layer, and it's basically glass, right? So now to remove glass, you will use maybe not the acids, you will use maybe plasma etching. So you create a plasma, and the plasma will remove like this layer. Or maybe you use polishing. So you just polish the chip. That's a valid technique. Doesn't work very well with very aggressive nodes, but why not? Or you can use there are other techniques like broad beam ion milling machines. So it's a beam of ion that will basically etch material away. So you do this, but your layer is gone now. So the passivation is gone, and you see now the top metal layer. So you see tracks basically. And those tracks are metal, so copper or aluminum in general. And so you make the pictures, you take your pictures, but then you need to get rid of this layer again. So same thing, you have the choice, sorry, between acid, so wet chemicals, dry chemicals, so plasma etching, for example, polishing, so in general it's called chemical mechanical polishing, CMP, or broad beam ion milling again. Okay, and it's just a repeat now.
And laser as well?
No, I don't use laser. Laser can be used for removing a part of the package, for example. But I'm pretty old. I'm old school. I like to use the acid. I'm used to it. So we don't use the laser for this. So we use lasers at the office, but for other purposes. So, for example, if you want to inject a fault at a given location inside the device, laser fault injection is a good technique. But for depackaging, no, we don't use it. So I would
Okay,
say we use laser at stage 4.
okay. We'll come to lasers later then. So
Yeah,
step one is done, the deconstruction is done, and then you have the layers now.
yeah,
Now
we have
step two.
pictures. Step 2 is going from pictures to schematic, because I cannot read pictures. I mean, like I see things, I would see memories, I would see the digital logic, the analog circuitries, stuff like this. But I don't know what they do, how they behave. So I need to get like from those pictures to basically having a schematic, or maybe the binary of the ROM, for example. So for this, we have a software that has been developed at TextPlane. So it's in-house special custom software that's basically helping you to do a number of things. So it will help you to stitch the pictures together for one layer. It will help you also to align the layers together. You have to know that in general, SEM pictures, so scanning electron microscope pictures, they are a bit distorted. So our software will correct the distortion, so you can really stitch the pictures together horizontally on a layer and vertically in the stack. But if you can do this, now you have all your pictures aligned properly for all the chip. And now we use the software is using feature extraction techniques. So machine learning based feature extraction, fancy machine learning word. I needed to say it. But the idea is now, instead of having pictures, you have vectors. And those vectors are representing all of the routing, so the upper layers, but also all of the transistors, the bottom layers, so the active part. Okay? And then the software will convert this into two things. It will give you the mask. So it's a GDS2 file. Basically, that's the files that you send to the factory to produce the chip, in a way. And it will give you the schematic in the form of a VHDL file. So it's a format to describe the chip internals, but you can simulate this. Okay, so that's phase 2. So going from pictures to those two files, GDS2. So the GDS2 can be used to check for backdoors, supply chain security evaluation. And the schematic now can be used for, I don't know, finding how to dump the chip out, or finding stolen IPs inside, or you name it. So that's stage 2. Stage 3 now would be to analyze those files. Okay, so when we are speaking about like digital forensics, that's the thing we do the most. We want to extract the memories, encrypted memories and stuff like this. So we want to basically understand where to get the data in clear, because in general, the memories, at least for the chips we are looking at, the memories would be encrypted. So we are looking for a way of finding the clear data bus inside the chip, and some ways to get like some kind of privileges. So the thing I'm talking about is being able to change instructions on the fly. So that's a very good thing. Your chip is doing something, but suddenly you say, no, don't do this instead. So you take control in a way. So changing the instruction. Skipping instruction is a superpower number 2. So an instruction you don't like, you just skip it. So it's also pretty good. And the third thing that we want to find is a way of like modifying the instruction flow. So this time it's like, I don't know, I give you the example of you have a conditional branch, but you want to be the one that decides which branch you take. Okay? So when you have found those two things, so the clear data bus and the way of changing the instruction, skipping instruction, and modifying the instruction flow, then you would say, okay, I can design now an attack to get the secret out. Okay? And that's the end of the stage 3, so the netlist analysis, I would call this. And stage 4 now is the actual extraction of the data. And for extracting the data, now it's back to the lab in general, and you have like different techniques. I think like because we are in a podcast, you want to hear about the most impressive one. I would say the most impressive one would be to modify the chip. So now you would use what's called FIB, so a focused ion beam. A focused ion beam is like a scanning electron microscope, but the beam now is ion. And you can inject gas on top of the chip, and it will interact with the chip surface and the beam itself. Okay, and this interaction makes it possible to alter the chip. So basically, you can cut some tracks, or you can connect some tracks together. So during the phase 3, you found, for example, that if you create a short between two tracks, now you get all of the superpowers I was talking about. Okay? But now you need to do this. And the FIB is basically used to modify the chip to reach this stage. Okay? And on top of this, you can also put pads on the chip surface that will connect to your clear data bus, for example. And then you would use microprobing techniques. So you would come with needles, you would put that on the chip to be able to listen to what's going on the clear data bus. And you would be able also to do all the things I was speaking about, skipping instruction, changing the instruction flow, or modifying instruction on the fly. So that's stage 4. So you modify the chip, you put your needles on it, and suddenly you extract the data, and you extract the data in clear. So that's the most advanced things, but any glitch can work, because now you can also say, oh yeah, I can maybe shoot here with a laser to change what's going on, and it will give me extra privilege, access to the flash memory, for example. Or you can use EM attacks. I mean, you name it. But the FIB modification and microprobing, I would say, is the thing we do the most, because the probability of us having a success in the extraction is almost 100%. It's just a question of time and motivation. If you give me enough time, I would say I would succeed. But sometimes it's pretty long. But yeah, I mean, it's difficult things, because like when you modify the chips, maybe you need to contact a track which is maybe 100 nanometer wide. Okay, so it's very small, and you can also kill the chip in the process. So you need to be very careful, and you need to have the 3 steps done before. So doing like step 1, step 2, 3, and 4 is taking some time. But if you are really motivated, that should be a safe way to get to the results.
Okay. Okay. So when you say change, is this change persistent? like you mentioned, you use focus ion beam, or you'll use tiny probes. Are you monitoring and then changing something on the fly, or is this a persistent change? Like the
Depends. This is really case dependent. So in general, I like to keep like the chip in a state where it can still run normally in a way, you know. But sometimes you make modifications that are permanent. It depends. It's really case dependent. This is where like the stage three, like the netlist analysis, is dictating what you will do at the end of the day, and you have the two options. But in general, I would say that the change you make you try to have a change that's not persistent like this. You can decide, okay, now I will do this, or I will let it run like in a normal state, you know. So I think it's better when you have more options. So non-persistent change are better in a way.
Okay, so tell me if I'm wrong. So you look at
what you've extracted, the code, and then
you map it to the chip at a place, at a specific place that you want to.
let's say you're looking at a branch and you say, okay, I want to change the logic of this branch.
Yes.
And then you map it to the chip and say, this is where that logic is being executed. Or
Yep.
Okay, and so
what exactly are you changing when you say tracks? What exactly is it?
It's tracks. In general, what you do is you isolate the structure. It could be, I don't know. I would say like interesting registers, like the PC counter, maybe the instruction register, or this kind of like things that are quite powerful inside the device. So you want to get access to them. So this is where you would put your pads. So the pads are there, but if you don't do anything, the chip is still running normally. So this is what you try to change, and this is really tracks. That's the physical track. So basically, I was speaking about like the passivation layer, which is the protective layer on top. You want to make a hole on this thing, and you want to dig until you reach the track of interest, and then you want to fill this hole with metal until the chip surface, so you can put your needle back on, and then you're ready to go. It seems very easy when you say it like this, but this is it, So imagine a PCB that you would cover with a plastic sheet, and suddenly you say, I want to have access to the track. So first thing, you make a hole in the plastic. Second thing, you put a probe on the track. That's what you do, but you do this on a scale which is like very different from a PCB. So small.
can you explain a bit of
Be careful. Again.
So can you explain the part where you have the image? What exactly do you see in the images, and how do you map that onto VHDL or code?
Yep. So the pictures are looking pretty, I mean, like pretty simple in a way, like most of so I need to make some differences between the layers. So you have like what we would call metal layers, which are tracks. So if you look at the PCB, that's what you would see, it's way denser and way more complex, but that's basically it, so you see lines going everywhere, that's the metal layers. But in between two metal layers, you have what's called the via layers. Again, like on a PCB, it's just like small plugs that would connect the two layers together. So when you look at pictures of this, it's only like in general, the pictures are black and you see only dots. Toot, toot, toot. It's all the vias. So that's the via layers. And then when you look at the bottom layers to get like the transistors and what's called the standard cells. So the standard cells, you can see this as the logic gates, like the NANDs, the inverters, the flip-flops and stuff like this. So you would see like structures that would be a bit more complex because it's doped silicon with polysilicon for the gates of the transistors and contacts that connects the whole things together. But same thing, our tool is basically from the pictures classifying the different cells. So then we can say, okay, this is an NAND, this is an inverter, this is a flip-flop. And basically, then the tool is just looking for, okay, I have this cell, I have this cell, I have like, I don't know, 300,000 cells, 1 million cells, and I'm just looking the other layers to know how all of this is interconnected. So basically, you can see this as a kind of a gigantic graph where the nodes would be the cells, the logic equations, and then all of the tracks and VI would be just the edge between the nodes. So that's a gigantic graph. The VHDL file is a graph, basically.
Wow.
It's big.
And that's certainly not possible through a manual process, right? Like you can't.
Oh, no, no, no. So, it's funny because in March, that's gonna be 20 years of me doing this. But 20 years ago, doing what we are doing now at Explain with like netlist extraction and things like this, that was not even an option. We would be like stitching the pictures with Photoshop, and then we would trace some part of the schematic on paper on the floor. It would be a mess. And the chip were not so complex as today. So you would be able to do a small part of it, maybe enough to construct your attack. But if you do this nowadays, good luck. I don't think you would succeed without like a tool that is making it possible. So that was our motivation when we created to explain was really to say, okay, it's a complex process, but it's very useful because now it can give you like ability to check the silicon. And again, I think it's a strategic asset, and more in this world. So we needed to have like some kind of a tool and processes that we could provide to the customers. So that's the whole idea behind what we did.
Nice, nice. And you mentioned that you have to take images of all the layers. How do you do that without destroying the upper layers? Like, is the process like you take an image of a layer, then remove it, then take the image of the next layer, then remove it? Is that the
Exactly.
process?
Exactly, yes.
Okay,
Layer by layer.
so doesn't that mean that the chip will be destroyed by the end, by the end when you
Oh, yeah.
reach at the end? So you
Exactly,
would,
yeah.
so that means that this chip is waste. So you would need another chip where you can decap and then put your probes or do whatever technique you want to use to be able to bypass the logic in the code.
Exactly, yes. So stage one of the four stages is destructive. So getting the pictures is you destroy chips. And you have to deal with it. It's life. Chips are meant to die in the lab. And so yes, you take pictures, you destroy the layer, take pictures, destroy the layer, and go for the bottom layers. And when you reach stage four, when you have to modify the chip, this chip has to stay alive. So you need to be extra careful now because you need to get access to the chip. So you need to take it out of its package. In general, you need to rewire it to a PCB or something, and then you need to modify it. So modify the chip with the focus ion beam, and then you need to microprobe, and the chip needs to be alive the whole time. And that's also a challenge. Sometimes, let's say, sometimes it's a challenge. Sometimes it's okay. Sometimes it's a challenge.
But this process, the four-stage process that you mentioned, and it's
Doable, like
you do it for a living, right? So doesn't that open doors for companies to be able to steal IP? You
Oh yeah,
have a chip, you have a competitor,
completely. Yeah, yeah.
you
Right.
reverse engineer, and
then you have the code, so you know now what it does. Right?
Exactly. Yeah. I think the best example of this is the printer cartridges. So when you buy like a printer a cartridge, which is like a off-branded product, what could have happened before is some people, I would not give names or anything, but some people would buy like the genuine device. They would go through all this process of like deprocessing the chip, taking pictures, reconstructing the netlist, and then they would extract the memories. And once they understand how the firmware and the hardware works, they would just like emulate the thing. But now they don't they can produce their own cartridges, and they can sell it for a cheaper price, and suddenly this is it. So reverse engineering chips I think the biggest market is this for the bad guys. It's I mean the bad guys. In a way, it's kind of legal. I don't like it to say it's legal because I still think it's some kind of theft, you know. But this is what they do. They clone the chip. So they take the chip and they do the same thing because they have the knowledge of firmware and hardware. But you can imagine whatever other thing you want. Like let's say you want to sell video game controllers. They would be protected by a secure element. Well, just dump the secure element and clone the chip, you know, or emulate the chip with something else, you know, and you would be good to go, you know. So that would be use cases for the bad guys to generate quite some money, I would say, by using those techniques, you know. Older case would be pay TV. In the pay TV industry, you would do kind of the same thing. You would try to understand how the smart card would work, to be able to modify it or to produce emulation that would have like more rights, you know, like no end for your subscription, all TV channels and stuff like this. So it's all techniques in a way. People were using like cheap reverse engineering 30 years ago already, you know. But it's still there in some ways. And what changed over time also is like with company like Explained, in a way, we provide those kind of capabilities for people that wants to do the right things. You know, like let's say you have like secure devices, I don't know, like encrypted USB keys or secure phones, smartphones, and stuff like this. And let's say you are law enforcement agencies that want to extract evidences. Well, sometimes it's difficult to get access to the clear data. And you would need, so before you would say, I will extract the flash, you know, and I would put this on a reader and that's it, you know. But with more encryption, more security in a way on those devices, maybe now you need to go to at the chip level to understand and to extract the data. And this is where we can be useful also.
Hmm. You mentioned Netlist. Can you explain for our viewers like what is the purpose of the netlist? How do you generate it from the chip, and what exactly is it?
The netlist is basically the schematic. So it's written in a specific format that basically describe every of the logical gates, the logic gates, and then it will say, okay, this is the list of all of the gates on the design, and this is how they are interconnected. So if you look at this file, it might be difficult to read, to be fair. So one step of the netlist analysis could be to try to hierarchize the information. So you go from something flat where everything is described, you know, like cell number one is connected to cell number two, then it's connected this way, that way. But if you can hierarchize the information, you go from like this flat netlist to something that would be what's called the RTL netlist. So basically, it would mean that you have like now the register identified and the operation between the registers identified also and stuff like this. So now to read this netlist, it's way easier because you have some kind of structure that starts to appear. Uh, this is a difficult task also, and this is also something we are actively working on because it's mandatory for some of the things. You are mentioning like IP theft. Yes, of course. I mean, like IP theft can be a thing. If you can like find how a chip work, you can copy this, you know, in your design. So that's the definition of IP theft. On our side, we want to we want to be able to prove it. We want to be able to say, if somebody comes to me and say, I think we have this IP that's our IP, this is how it's defined. I think my competitor copied it into his design. So now you would need to be able to take this netlist, so this schematic in a way, you know, and to hierarchize it to the point where you say, okay, this block, that's your IP. So it's been stolen. So now you can go in front of a court, but you have evidences that it has been stolen because that's a difficult topic. I mean, like this is not an easy task again, but that's very useful for those companies that are, you know, dealing with IPs. You know, so if you can just like copy paste the IPs from everybody, it's really bad. You know.
So you create the netlist from the images that you
take. Yeah.
Sorry, I didn't get it.
You,
So you can generate the netlist or create the netlist from the images that you take of the
Yep.
layers. Yeah.
Yes. Yes.
Okay. 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 Interesting. Interesting. Okay. And you mentioned that, people haven't been doing it for 20, 30 years. I think one of the primary reason of the hardware industry, uh, is it true that it started from Europe when companies created the smart cards, the chips, and then people started hacking them? Is that true?
Yeah, I'm not sure of this. I wouldn't be able to tell, like uh, uh, it's a very complex topic now because like all those things that happened in the past, and I can refer to pay TV because I worked a bit in this field, but even in this pay TV world, some stuff that was happening in Europe was also happening in North America at the same time, and now it's difficult to know who was first and how it was working, and some of the stuff are probably not public still today, so. I wouldn't say anything here because I would be scared that people would get pissed at me, like, oh, you're saying bullshit, I was the first and
Yeah.
stuff like this.
Yeah.
So,
Yeah. But you would say, for example, from software side, when we had Microsoft, Windows and Linux operating systems, then that's when researchers started looking at, identifying issues like, oh, there's a vulnerability called buffer overflow where you can do this, and you can overwrite the PC address to execute any random code. So that kind of started the interest in the research community in security. Do you think that from hardware security perspective, was it the smart card industry that got the interest of researchers, where they sat down and they thought, wait a minute, let's try and see what's inside this chip, and maybe was that the kind of start of the whole the hardware security research community?
maybe I see this in a bit different, but I can be completely wrong on this. So the way I see it is more like so smart cards were introduced and stuff like this. Okay, it might have attracted already some of the researchers. I think it did, but I think it's more like the the piracy that started it, that kicked the whole thing in, like people wanted to have free TV, for example, So suddenly they had to hack the card, So because now you have like the attacker side becomes relevant, the defensive side becomes also relevant. So I don't know what was first, but the way I see it is very like something that's driven by money, like I want to hack this thing because I can make money out of it, So I do it, and then people research. The thing is like not so many people can research things inside chips, because of all the tools and equipment and software things that you need to develop to get to the point, It's the barrier of entry is pretty high in a way, So I would say that yeah, the thing that started it must have been money, so piracy in a way, So I see this way. I can be completely wrong. So don't say this is the truth that Olivier is talking about. I have no idea. This is the way I see it. And still today, it's still complex. Like if you are a newcomer and you come to me and you say, "How do I start this?" And I say to you, "Oh yeah, that's very simple. You need to have like wet chemicals, dry chemicals, scanning electron microscope, FIBs, microprobing station. You need to develop a tool for a few years, to be able to go from pictures to Netlist and blah 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 blah." You would say, "Hey, don't start," So it's a lot to and it's very different from the software security. I'm kind of jealous, of people that can say, "Oh yeah, I can work in a plane. I have my IDA Pro license. I'm in the plane. I reverse my binaries and stuff like this. It's luxury, I need a lab, So it's a very different situation for me."
How did you get into hardware security? Like, where was your starting point? Were you forced into hardware security, or were you like, okay, this looks interesting?
It's I don't know if I should say this. I would say it's a life accident. Uh, because I was like, so my background is microelectronic design, uh, analog design on top of this. And after my engineering school, I was looking for a job and couldn't find one because it was like not the right timing for the tech companies. It was a pretty bad time. And at some point, my girlfriend at the time is showing me an ad in the newspaper, and the ad was, "You want to fight piracy? Call this number." I called, got the job, and here I am. So it's really an accident. But
That's
yeah, I
quite
mean,
interesting.
I enjoyed it. Like I was already like this kind of guy that was like making like I was not a good designer because I wanted to find ways of making the design not work, like finding glitches, finding like way of abusing the stuff. So I was not a good designer because of my interest in like things not working. And so when I found this job, so 20 years back now, I was blown away. I had no idea of like all of this existed, like scanning electron microscope to hack devices and stuff like this. It was like, wow, that's so cool. So yeah, so I was very enthusiastic enough that I started to explain and stuff like this. So, but yeah, it's a yeah, I don't know, luck.
But initially, when you started, um, maybe on your own, when you didn't have all the equipment, how how I want to understand your experience when you have nothing, right? And you're doing something, right, which requires pretty expensive equipment. How did you manage to survive?
So this is where I was very lucky on top of the other things, because so this work when I was like calling for this ad in the newspaper, I arrived in a lab where there was a scanning electron microscope, a focused ion beam, plasma etchers, wet chemicals. The whole thing was there. On top of this, the team that was there was awesome. Like the very expert guys, like it was a blast. So it was kind of funny at the time to say, oh yeah, we have all those equipments, and we have guys that have like the knowledge to be able to do the things, and suddenly I appear, and I mean I was working probably 10, 12 hours a day, when I could, because I wanted to learn this, because everything was there. It was a game. It was a game for us. It was like we had smart cards to dump basically. So we were in the pay TV field, and we were getting like the pirate cards, and we were trying to extract the firmwares to understand what the pirates would be doing. So it was a game for me. It was a game for everybody. So we were not going to the office to work. We were going to the office to play this game of trying to get like the code out of the pirate devices. So that was a blast. So I did this for some time. And the motivation for me to create my own company was the software side of things, not like analyzing the software that we would dump, because I don't do this, but to get like some kind of tool that could like go from pictures to Netlist to archives Netlist to analysis and the whole thing. Wanted to kind of like automate the whole process good enough that people would be able to do this themselves. So again, it was kind of a very very exciting times. I have very good memories of my first job in this pay TV thing, and then creating Texplain was just the follow up to say, okay, so we go from like I know the techniques, but now I design something that will make it possible to scale this up. So that's the idea. So it's a very particular way of life in a way, because I mean, like, if you want to start this nowadays, I would say find a good university where they have the tool already, and learn from this. But you would not start on your own. It's difficult because I mean, like if you have like money enough to buy the equipment, good for you, huh? But I don't think it's possible nowadays. Huh? 30 years ago, that there would be like some pirates that would have the equipment in their garage or in their kitchen or whatsoever. You know, you would come to their place and it would be like nonsensical, you know, equipments everywhere, and very clever people like dumping chips. You know, so yeah, it changed quite a lot.
I still know a lot of people who have a lot of equipment in their backyard.
I knew some of them.
Yeah.
Oh, so
Let's say somebody who is already finished universities, working somewhere, and gets interested into this field. What would your suggestion be, as in how would that person go ahead and start a career in this?
I would go law enforcement agencies, to be honest, because they do this now. And yeah, so if you have the skill, you should be. I mean, it's still pretty rare to me. So you should be able to find a job there, you know, and start to apply what you learn at the university. Some of the big companies, the big tech companies, start also to do this to evaluate their own security. You know, so some kind of like red teaming the chip they produce, stuff like this. So that would be an option too. You know, but it's not gonna be an easy task to find a job because there will not be a lot of those jobs. It's still like a very niche activity, you know, in a way. You know, but I think it will grow. So you need to, you know, you need to be like willing to do it and be patient enough to go into it, you know. But then if you want to start doing stuff, you know, I mean, I don't want people to start hacking chips in their kitchen. It's too dangerous. So yeah, I got I got the case once, you know, because I'm giving, as you know, trainings at Hardware.io. So I explain all those things, you know. And once I got like one of my students that dropped me a mail 2 weeks after the training and said, "Oh, I decapped my first chip." So he sent pictures and stuff like this. And I'm like, "How did you do it?" And he's like, "Oh, I did this in my kitchen." And I was scared for him, you know, because I'm like, doing this in your kitchen, like if you breathe nitric acid, that's probably not very good for your health. I mean, not probably, it's sure, it's really bad. And he said, "Oh, no, but my window was open." And I'm like, no, but wait, if your window is open, the probability that the air is going inside is greater than the air going outside. So basically, it's even worse, you know. But so I don't want to have those people, you know. I don't want to have people like taking risk for it, you know. So, but it's difficult. What you can do if you really think you will be good at this, you can send me your resume. Yeah, why not? So that would be an option.
Yeah, yeah. So universities, forensic labs,
Yeah.
government R&D departments that
Yep.
do for various reasons,
Yes.
uh, chip manufacturing companies,
Yep.
Texplane,
Explain. Yeah. And some of
and
the OEMs. Some of
OEMs,
yeah, yeah,
OEMs as well.
yeah.
Okay.
More and
Okay.
more. I mean, like for the OEM, the situation is the following. You want to create a device and you need chips for it, you know? And now you will have like choices to make. Which chip designer, which chip do I buy, basically, you know? So when you look at the datasheet, they would all say the same thing. Our chip is 100% secure, no risk, you know? But it turns out that the OEMs, they don't trust this anymore. So they want to test, you know. So they might be doing only like side channel tests, or maybe they would go to glitching, you know, like power glitching, EM glitching, laser fault injection, stuff like this, you know. But some of them will go up to, okay, let's look at the silicon. I will have my firmware inside. I want it to stay inside. So some of the OEMs, the bigger ones, they would also do this, you know.
Got it. Got it. All right. So since you touched on glitching as well, fault injection. Can you speak a bit about it? What is the purpose of glitching? What are the different methods of? I know we briefly touched on laser fault injection very briefly, but yeah, please.
Okay, yeah. How do I define glitching? Glitching is the fact that you will disturb the chip in a way that will change the values of some of the registers. I think that's the simple definition. But then, what does it mean? So the idea would be to get like things like skipping instruction because you glitch the chip, or maybe you want to read something from the chip, but you change the address because you modified something, and suddenly you read something else, so you start to extract data, or you name it, so you create some kind of a disturbance that gives you an advantage. And now to do this, now you have a wide range of options because a chip is physical, so everything can work there. So if you look, for example, the threshold of the transistors, so the transistors, those are switches in the digital domain. But the threshold might be dependent on the supply voltage. So if I change this supply voltage, I change the threshold. So if I change the threshold, I might be able to register like some false value, wrong values inside the device, inside registers. That's glitching, basically. So this is a glitching. Laser fault injection. So laser fault injection is more precise because instead of changing everything inside the chip or having an impact on potentially every of the transistors, you kind of choose where you want to inject the faults. So you have a beam that's maybe a bit more than 1 micrometer wide. So you would touch like several transistors, but still it's localized compared to VCC. And when the laser will reach the silicon material, so the semiconductor material, it will create basically, so I don't go in the details of like, I was about to go in the details, but it will basically um, make your switch be active without the need to control the switch itself by the circuit. So it's the laser that will open the switch or close the switch instead of like the chip itself. So basically, you can also inject an error somewhere, but in a more precise manner. But then everything can be used to glitch. So EM, electromagnetic glitching, is a thing. So same thing. If you have an electromagnetic pulse, well, it will impact the chip. You might have errors, and that's might be something useful for the attacker. The whole thing with glitching to me, I think there's a drawback to this. We don't glitch. I mean, we glitch also, but the big difference between microprobing and glitching to me is when you microprobe, you expect some results. You can almost predict what's going to happen. When you glitch, well, you fish in a way. You try to find something that is creating an error inside the device, but then you expect the error to give you an advantage. So it means that now you need to solve like a few things. So when to glitch, what's the glitch waveform for VCC glitching, where to put the laser for laser fault injection and stuff like this. And this is where you can see that if you can extract the firmware with invasive method as we do here, you have extra information. You know the firmware, so you can try to find the correct timing for injecting the fault. You maybe also know the hardware, so you know where to place the laser and stuff like this. So to me, all those techniques are things that you combine, like invasive attack, glitching, side channels. It's all things that can be combined. And yet there's a learning curve. So at the beginning, you know nothing about your device, about the chip. And at the end, you say, oh, I know the firmware, I know the hardware, I found like this many glitches. So now I can combine. And if I see this on the side channel, I know the glitch was effective, so I can do this and that. And you expand. So I don't like evaluation where you evaluate one thing and you don't think about the rest, because to me, especially if you have an attacker that can do what we do here, it can glitch also. So you need to combine the whole thing. You need to think of all of it. That's also why it's very difficult for chip vendor to have a secure design. It might be very difficult. I prefer to be in my shoes. And so, yeah.
The laser fault injection technique, is that also temporary, or does that damage the chip?
No, in general, it doesn't damage the chip, but in some situation, you might still kill the device. One example would be, let's say you have like a value inside the flash memory, and the value has some kind of a checksum or something. And now when the value is red, you change the value, but not the checksum. The chip sees it, and it's a security violation. So maybe the chip, I don't know, maybe it's a smart card that says, okay, in that case, I'm under attack. I erase the flash, nothing more to extract for the attacker. So you can still kill chips. I mean, like I remember, like I think it's one of the first thing I was doing when I started in 2005, a laser fault injection, and I would kill like 20 chips a day, at the time. So I would spend the morning preparing the devices, and I would kill them all in the afternoon. So yeah, but if you know where to put the laser and so on, should be safe.
So what is, or what are some of your best attacks, or findings?
I can't say it. Oh my God. No, no. So yeah, all we do are under NDA, but I was speaking about something earlier, like hidden modes in chips. I would say
Yes.
that's the coolest thing. When you find this and you find the way of accessing those, suddenly you are not trying to dump the chip anymore. You're just trying to go in this mode, and then you send the command, a stupid command, and suddenly it's the chip that gives you the code. Oh, this is what I have stored inside the flash. It's all decrypted by the chip, and it's beautiful because now you see all the data, on your logic analyzer or something, and you're just like, okay, done. And in general, there are also like attacks on JTAG, re-enabling JTAG chains to get access to internal structures and stuff like this. But in general, I would say that the attacks we do are so difficult and long that the best thing is the moment, the 5 seconds where you see that you reach the results. This is worth it. It's 5 seconds of like excitement for months of work, and that's okay for me. I like challenges, so. But then I can't be more specific. People will not like it so much.
What would be, in your view, what would be the motivation to have these hidden codes, or uh, backdoors?
Uh,
Eh,
do Usually it's from the manufacturers themselves, right? But when you have JTAG protection,
Where only authorized, you can have an authorization, right?
via JTAG, then
Why would somebody go ahead and still have hidden commands or codes?
inside
Again, it's very chip dependent, but I think like it makes sense now for chip vendors to have like some kind of scan chain, like a JTAG or something else. I mean, like something, to be able to write their code, maybe debug, test, do failure analysis, and things like this. So it gives an opportunity for the attacker because you see this, you know it's there. So if you can just like open this again, now you have access to everything. So it depends on the chain again, it's chip dependent, but it gives you access to a lot of resources, internal resources. So it's a good motivation for a lot of different topics. I was speaking about cloning, piracy, um, you know, you name it then. Huh?
Mm, mm, mm. So you think that
Manufacturers still have
these hidden stuff
for legacy reasons, or are they continuing to do it, or are you seeing new chips which do not have this hanky panky stuff?
They need to have something. So if they don't have JTAG, they need to have a mode to program the chip. So because they need to put data in the first place. So for them, they don't have a lot of choice at this stage. They need to have a way of accessing the internal resource themselves. So that's there. Sorry, I don't remember the beginning of the question. But yeah,
But I guess,
I see improvement. I see a lot of I see a lot of effort is done to protect the chips. Like they put sensors, they put like sensors for laser fault injection, for example. VCC glitching sensors, you know, like they look for the power filter and try to detect the glitching pattern and stuff like this. So they really try, you know, they try to secure the devices, you know, but it's difficult. I mean, like, again, I don't want to be in their shoes, you know, because the fact is, if you have like people that can take like all those pictures and convert this to the schematic, now you are aware of the protection. So for example, I wouldn't put a laser beam on top of the sensor that will kill the chip, you know. I would put it somewhere else where it's useful, you know. So um, it's a cat and mouse game anyway, you know. So it's getting more complex for the attackers because the vendors are actively working on the topping, but at the same time, the attackers are also like learning stuff, you know. So it's difficult. It's difficult to secure chips, I think.
Are there any standard ways for protection against fault channel, fault injection? Sorry.
or it's difficult because
I think it's difficult. There are ways. There are like some kind of like I would say a library of good practices and stuff like this. But then it all comes to do you do it yourself? Is it an IP that you buy to you know like a security IP? You know you put this in your design. Do you care about it? There's some chip vendors they would say "Well, I don't care. You know it's okay. I will not be facing this kind of threat or something like this. So it comes to what the chip vendor is doing in his threat modeling. So if my threat model says I'm not gonna be attacked, I wouldn't protect the device, you know. But I don't know, and I mean, if this is someday, I hope I will have the opportunity to design my own CPU, you know, because knowing knowing how I would attack it, I can be sure that I would be very sneaky, you know. But um, then again, like looking at different chip vendors and different chips and stuff like this from different generations and stuff like I see a lot of like efforts to try to protect the chips, but I don't find something that will prevent the attacker to succeed if he puts enough like time and effort.
Yeah, I mean,
I mean,
yeah, see,
you can't do it. Security like 100% security, it doesn't exist.
yeah, yeah. Like if you, I mean, I'm not able to understand the protection mechanisms. For example, you have, let's say you're in the code, you have a branch, or you can say if R0 register 0 is 1, then do this, else do that. And if you are injecting a fault, either EM or laser, how do you protect against that? Like the value can change, right?
Yeah, exactly. Yeah. So I don't know. You can do this test multiple times. You can duplicate this part of the circuitry and do some kind of like check that everything is the same. Or you can try to find the attack itself. So, for example, you put a photodiode close to this structure and some kind of a photodiode, of course. And then if it sees light from the laser, it would say, "Oh, security violation." It's a combination of all of this, you know. So you try to increase the complexity of your thing. You try to have redundancy. You try to have the right sensors. If it's something that you really need to secure in a test like this, you do the test multiple times just to confuse the attacker. You use random delays. So you don't want the same operation to happen always at the same time. So you try to have random delays. So this test is never at the same time. So for the attacker, it needs to find when to glitch. So maybe he needs to glitch the random delay. So now the time becomes fixed to glitch again the instruction. And you know, you try to make it difficult, you know. So there's no good method, you know, it's a combination of things again.
Yeah,
Eh,
but there's still no guarantee that. Mm.
no, never. Yeah.
so what do
Yeah.
you do when you are what do you do when you are not hacking chips?
I'm
I
hacking
know
chips a
you
lot.
party a lot. Yeah.
Yeah.
So yeah, I really love to be with you partying after your training, especially. But in
Yes.
general, what do you do when you're not?
You mean in life? I don't know. I like to go kayaking a lot. Be alone on the sea, or on a river, or whatsoever, and listen to music and look at the beautiful world, around me. I like to party a lot. That's true. I don't know. I'm playing some video games. I started again. I was playing more when I was a teenager, but it turns out that I don't know. Being with friends, usual things, I would say. I don't want to say too much too, but yeah,
So
normal life.
so
But I hack ships a lot. I still do this. Still something I really enjoy.
so parties in US or parties in Netherlands or parties in France, which would you choose? So in US, I mean, the Bay Area.
Yeah, yeah, yeah. I don't know what to choose. It's a tough question. I mean, the parties in France, of course. I'm kind of expert in partying in France, so it's pretty good. Uh, Last hardware IO in Amsterdam was a blast. We got like some amazing parties with the guys from Ninja Labs, and some other guys. It was like was a blast. It was really good parties, especially last day. I think we didn't sleep the last night. And with you, I mean, like it was a crazy night. But yeah, the Bay Area, I like it too, but I wouldn't be able to classify, but they're all good at the end. We make them good. So, yeah. What's your favorite ones?
With you anywhere.
Same answer.
All right, maybe I'll share some photos in the podcast
No,
itself.
no.
Please check these photos.
Uh.
All right.
No, no, this you can't do this. I will have to look at the pictures I have with you too, and then you don't want to start this war.
All right. I'll filter some of the photos, send it to you. You approve, and then I put it in the podcast.
Yeah, maybe. Yeah, maybe. Okay, can do this. Yeah, but don't do like non-responsible disclosure. That's not good.
Sure, sure. So, all right, Olivier, thank you so much for this podcast. I think I learned a lot from this. And I know for sure now that I'm not going to go into chip hacking because I don't have that expensive equipment. But it's a really interesting field. And yeah, thank you so much
Thank you for the
for joining
invitation.
us.
It was fun. I really enjoyed it. We have the same kind of color of t-shirts, and again,
Yes,
Mario,
I have the exploited t-shirt.
nice. Yep. No, no, it was very nice to be invited. I hope I didn't say like too much bullshit, or at least that what I said was clear. But you'll tell me. And you can come to my place. We will share the lab.
Definitely, definitely. This year.
Perfect.
All right. So we learned a lot of things today. For example, backdoors inside chips are possible. It's difficult to identify. Uh, it's a uh, it's a tedious process. Um you can reverse engineer the code of the chips if you without anything or any specifications about the chips, and obviously find a lot of juicy information and vulnerabilities inside of the chips. So thank you everyone. This is JHacker signing off from the JHacker show. Until next time.
Thank you.